All right, so we're moving on to Unit 5, Section 4, which is dealing with our sampling distributions and looking at them with sample means. Okay, so we're looking at sample means instead of proportions in this case. The main difference between your means and proportions, remember, proportions are like percentages, so you're dealing with numbers that are less than 1, 0 point something, while a mean can be any number. Proportions are great and really only used for categorical data. So if you're comparing two things, candidate A, candidate B, looking at grade levels, etc., male, female percentages, that type of stuff falling under categorical is what you would have. If you're dealing with more quantitative data, which is the measurements of things, how long something takes, how fast somebody is, etc. All that stuff is used for means because you're going to add, subtract, multiply. You can take those and you can manipulate those numbers themselves. Some of your notation stuff here, mu means is your population mean. So it's the population parameters, basically. Sigma is the population standard deviation. So it's what the actual standard deviation of the data is. And then X bar is the samples mean. So when you take a sample, whatever the mean is, that's the X bar. And then S sub X is the standard deviations from the sample. So these two are what you're really going to see whenever you gather any data, while these two are going to be your estimated values. They're never really found exact because, again, finding the population values are not easy all the time. Okay, going back to some of the stuff with proportions and the formulas. So the mean of a proportion is mu sub p hat, which is equal to p. And then your deviation for a proportion is using this square root formula, square root of p times 1 minus p all over n. And you take the square root of the entire thing. That is fine. But yes, it is, I gotta take this square root of this big thing, multiply stuff together. Means are a little bit easier. Again, the mean part is straightforward. It's mu sub x bar is equal to x. But the standard deviation is a little bit easier because you just take the standard deviation that is given to you and then you divide it by the square root of whatever the mean is. The larger that mean, or not mean, the sample size. N is sample size. So it's deviation over the square root of the sample size. The larger the sample size you have, the smaller that standard deviation is going to be, that sample deviation. It's going to shrink it down and make it more precise. Okay, so that's your formula to find the standard deviation. Normal distribution, x bar is equal to, or is approximately n, or similar to the normal distribution with this mean and the standard deviation. This is notation change. It's not anything new here. It's just a change in notation. Okay, the central limit theorem. So the central limit theorem is new for means. It's not used in proportions very much or at all. Basically, the central limit theorem states that the larger an n value, or the larger the sample is that you have, the closer the distribution is going to be to normal, to the normal distribution that fits for it. Think of this in a small scale. So if you're dealing with flipping a coin, if I flip a coin twice, I have three options. It's either going to be 2 heads, 2 tails, or 1 heads and 1 tails. So I've got my 3 options there. So it's either going to be, if you're looking at heads percentage, it's 0, 50, or 100. And every time you flip it, it could be, anywhere from there. The more you flip that coin, though, if you flip it 10 times, 100 times, 1,000 times, million times, what ends up happening is the larger that sample is, the more towards that 50 percentile, it becomes more common. And so it's more likely to occur, and then the extremes on either side are less likely to happen. And that's what basically the central limit theorem is stating, is the larger the sample, the closer you are going to be there. Rule of thumb that we have for our sample size, the n value that we want our n to be at least 30 or more, and then we usually say, yeah, it's going to be pretty normal. That's used when we talk about our normal part for our state plan, our plan part. So the independent, random, and normal, this is where we're going to be using it. So again, your example for your template, this is the same as what we've talked about before. So state, You're going to identify the population parameters in words, state what the variable represents. You're going to restate the problem and any other proper notation that's needed and other information. Again, this state part, I shouldn't have to read the problem to get the information. The state part should have all the information I need to continue. Plan, random, independent, normal. So random, make sure that the problem has randomness, simple random samples, etc. For that. Independent needs to be your 10% condition, or it needs to be stated that it's independent. Both are fine, but your 10% condition, which is the same that we had for proportions. And then normal, your sample size should be larger than 30. If it's not larger than 30, hopefully it says that the population is normal or normally distributed. If it's not over 30, your sample isn't more than 30, and it's not normally distributed or doesn't state that it is, then typically for this one, we either have to switch over to a different one using like a t value instead of a z, or if any of these don't get hit, we usually just state in it, this has not been met, we proceed with caution. Okay, and then in our conclusion, we restate that we proceeded with caution. So you still continue on even if they're not met, but you just want to state that, hey, this hasn't been met. Hey, red flag, and then continue. Your do, so you state your distribution, restate basically the problem you're trying to find, draw the distribution curve with the shading, so you're shading above, below, or the middle, and then find whatever the probability is. Make sure you show what the z value is in this part. Last but not least is your conclude, so you summarize whatever your findings are. Using a sentence or two, you want to state context, what was told in this problem, what it meant overall with it. Okay, so that's what you have in your conclude, is that you're summarizing what you're finding with the context. All right, let's do an example here of this one using our means. So here's our question. Suppose that the heights of young women are normally distributed with a mu of 64.5 inches and a deviation of 2.5 inches. What is the probability that the mean height of a SRS, okay, simple random sample, of 10 young women is greater than 66.5 inches? So we're trying to find what's the chances of, if you select 10 young women at random, that their average height would be more than 5.5 feet, 5.5 feet. So 5'6.5" inches taller or more. Okay, so that's what we're trying to find based off of this. So let's go through it. State, plan, do, conclude. Number one, we go through our state. So stating the information that we need. First off, what's the probability we're trying to find? So the probability we're trying to find is that the sample size, that sample mean, is going to be more than or equal to 66.5, which is that first statement there. So P is greater than, or P of X bar is greater than or equal to 66.5. Now, if you notice here, we actually haven't done a sample. We don't get like what the actual numbers are, because what we're doing is we're trying to find what's the probability of this occurring. Later, we're going to go, okay, this is the sample we got, and what's the chances of that happening? And we'll talk about that when we do confidence intervals and different things like that. Next bullet down is our mean. So we're stating what the mean is. The mean is the height of women. You could probably also mention what unit you're using, so you might want to say like inches in this, but it's not super important with that. Last three bullet points are the key pieces of information that you have. So number one is the mean of the normal distribution, the standard deviation of the normal distribution, and then how large your sample size is. So those are the three key pieces of information you need, or number-wise, for it. You also need to state what the variable represents and what probability you're trying to find. Okay. If you want to draw your image here, you can, instead of doing it under the third section, but you just need it somewhere. All right, next up is plan. So remember, plan, you're doing your random, independent, normal. So first off, random, it states that it took an SRS of 10 women. So because it states that they're using a simple random sample, that's all you need. There's nothing else you need to really justify with that. So because of that, we can say that the mean is probably going to be about that 64.5. Next up is independent. Independent is your 10% criteria. So is 10% of all the young women less than 10, or is the 10% of all women more than 10? The answer is yes. Or the sample size that we took, which is yes, obviously. So from there, we can say that the standard deviation is going to fall under that formula we have, which is 2.5, the deviation that was found from the normal distribution, all over the square root of our sample size. Remember, the larger the sample size, the smaller that deviation can become, because we have less variability with the larger sample. So with 10, that means we've taken it from basically 2.5 and we've shrunk it down to about 0.79. Last one is normal. So remember, normal is typically the size of the sample. You want 30 or more. This one's only 10, so it's less than. But in the problem, it states that the population is normally distributed. If you go back up here to this part here, it says that suppose that the height of young women are normally distributed. So right there, we do not need to have a sample size of 10 or of 30 or more. 10 is fine because it states in the problem that the distribution that we're working with is normally distributed. Okay. And that's our plan. So we hit our 3 points. That means we can proceed without having any caution. We're good. We can continue. Next up is the do. So the probability of x bar being greater than 66.5, which is what was stated back in state. We mentioned what our normal distribution is. So our normal distribution is the 64.5 comma 0.79. That's that deviation from what we found here after this calculation, okay? Because we've taken, instead of the deviation of the entire population, we're going, okay, for our sample, we're going to narrow it down and make it smaller. Now when we do our z, remember you got to find your z values on this. Rest of it you can do on your calculator where you're using normal CDF, normal PDF, or normal CDF, etc. On your calculator to find this, you need your z value though. So your z value has to be greater than or equal to 2.53. So it's just 66.5, which is the value we want up here, minus the mean that we stated here, divided by the deviation that was calculated of 0.79. Gets us a 2.53, which means we're about 2.5 deviations above where the mean is. And if we find that probability of you getting a sample where the mean is larger than 66.5, it's actually less than 1% chance of that happening. So it's about a 0.57% chance of it happening. Very small, very small, very small. Okay. And once we've stated that, you can also have your drawing there showing the shading for you. Last thing we do here is that we write our sentence concluding what we just found. And our conclusion that we found was that the probability of the average height in an SRS of 10 women is greater than 66.5 inches is 0.0053. Or it's extremely small. You can go into a little bit more detail if you want to talk about it. But this is basically enough to do your conclusion. It's stating the context of the problem. It's talking about the height of young women, or women in this case. It's talking about taking your sample. It's talking about what your range is, so more than 66.5, and it states what the probability is. So it's got all the information we need, one sentence. If you can't write it in one sentence, don't think you have to. You can do it in 2 or 3, however many you need to get your point across. Okay, just make sure it covers the main things that you need. All right. Okay, that's the end of this one. We'll do obviously more example problems of this, but that's the end of this one of introducing our mean values for quantitative data. The next one after this is dealing with multiple, or the differences of our quantitative data. So if you got 2 means and you're trying to find the difference of them.